We've just spent a lot of time talking about the SN2 reaction, bimolecular nucleophilic substitution. And I said that the way it works is that we have the bond to the leaving group breaking and the bond to the nucleophile forming at the same time, that this is a one-step reaction. And there are lots of consequences to it being a one-step reaction. We know the stereochemistry, we know the rate law, all that kind of thing. It didn't need to be that way, and I want to take just a second to think about why it's not one of the other ways. So again, what we need to do is break a bond and form a bond. And there are essentially three different ways that could go down. They could both happen at once, which is what we kind of consider the SN2 reaction here. There is another scenario where I make the bond to the nucleophile first, and then have some intermediate that then falls down. But again, I really hope that you feel just a visceral revulsion to this. This was bad, and it made me feel bad to put on the whiteboard. Why? I will tell you why. Carbon takes 4 bonds. This has 5 bonds. That's not a thing. Not a reasonable pathway. Which leaves us with the last possibility. Break then form. So in that possibility, in the first step, I break the bond to the leaving group. Right? These electrons go with the leaving group, and so I'm left with a cation here and an anion there, the leaving group. That cation is relatively reactive most of the time, and so in a second slower step, the cyanide could make a bond with that cation. Now you might say, what is to prevent it from just recombining and going backwards in this case? And the answer is nothing, right? In theory, you should definitely sometimes just have that bromine go back and make a bond, maybe even most of the time. Okay. So, like I said, we put a lot of effort into explaining that this is how the SN2 works, but I don't really think I explained well why this doesn't happen. The biggest reason that it doesn't happen that way has to do with the stability of the carbocation intermediate. So these are carbocations. Notice that it's got a C plus there, but it also does not have an octet. There's no lone pair there, 6 valence electrons. It turns out that when you're thinking about how stable these carbocations are, which is to say, how easy is it for me to make them, right? The more stable something is, the easier it is for me to make it, the lower the barrier to make it. In this case, the more substituted the carbocation is, the more things around the plus, C+, the more stable it is. So tertiary carbocations, quite a bit more stable than secondary carbocations, way more stable than primary carbocations or methyl carbocations. So why is that? Well, it's exactly the same as alkenes, right? Remember, alkenes, we made the same argument. The more substituted, the more stable. And that's for the same reason, this hyperconjugation idea. So again, I can draw the fancy orbitals and say I have 2 from my filled sigma, I have some empty pi, and they can overlap and lower in energy. The non-molecular orbital drawing way to think about it is that this filled orbital can just lean over and give some sorely needed electrons to this empty p orbital, right? So it's a neighbor, it's basically overlapping it already. It sees that it's got no electrons and really wants it. It kind of just leans over and say, hey, I got you, fam. If it could talk and say fam. So that's what is happening here. The more substituents I have here and there, the more chances I have that something will be lined up at any given time to lean over and donate electrons to the carbocation. So more stable, more substituted carbocations are more stable. Back to reactions. So here is the reaction that we showed earlier. 1 bromopropane going to this nitrile. And we can identify this as an SN2 for lots of reasons. We can say, well, it's got a great nucleophile. It's got a nice leaving group that is unhindered. And so, yeah, that's going to be a good reaction. I look at this bottom reaction, if I were to ask you, could that go by an SN2 reaction, you would say, never. There are lots of things wrong with it. First of all, that is hindered as all heck. There's no way I can do backside attack to that, A. And B, there's no nucleophile. That's water. Water holds its electrons way too tightly. Water is a terrible nucleophile. And so this seems like the last kind of reaction that would happen. I'm here to report that this reaction is actually pretty fast. That this actually does, if I take tert-butyl bromide and add water to it, it is going to give me quite a bit of tert-butanol, especially if I heat it. How does this work? It works by a different mechanism. What happens here is that first, my leaving group leaves. That gives me a nice, stable tertiary carbocation. Again, because that's pretty stabilized by all these bonds on the periphery, it can be formed. It's a low enough energy thing where it can be possibly formed, unlike this cation here, that would not be formed. Okay, could this bromine just go backwards and make a new bond? Absolutely. This step is reversible. It's going back and forth pretty quickly. But there's also water around. Is water a good nucleophile? We just said that it isn't. But this is very reactive. Even though it's kind of the most stable of the carbocations, it's still not what we would call put in a jar and save for your grandkids type of stable. This wants to react very, very quickly, on the order of microseconds, if not shorter. And so really anything with a lone pair, like water, can come in and make a bond there. Now I'm going to have water acting as my nucleophile. Even though it's a weak nucleophile, it's good enough for this hot electrophile. Lone pair comes up, makes a bond, there it is. Notice that I did not have to say that water busts up into OH minus first. Okay? Those of you that took 116, which is pretty much all of you, know that this equilibrium is really, really small, right? Only like 10 to the minus 14 is kW here. So in pure water, there's very, very, very little OH minus around. Okay? And so please do not say, oh, first water has to explode and then attack. No, no, no. Water attacks as it is, and so the first thing you see is this H3O plus, or this O plus thing. Okay. So does it stay like that? Well, there's lots of things in the pot that could take that acid proton. Again, one way to think about this is the conjugate acid of this pretty stable alcohol, so it wants to get back there. Do I need a strong base to take this H? No, I don't need a strong base. That's a very strong acid. What weak bases are around? Well, there is bromide around that could take a proton, but that's really, really a weak base. I think water is even a better base than 3R minus. So I think that what you're going to have is, again, you have lots of water. It's your solvent. So you're going to have some H3O plus after that takes the proton from the alcohol. And yes, you'll have some Br minus floating around as well. In some ways, the reaction looks very similar to the thing we saw up here. We're starting with an alkyl halide. We are giving it some nucleophile, and the nucleophile is substituting for the alkyl halide. However, it's also different in a lot of ways, right? This was a one-step reaction, and this is, really, I've drawn it a three-step reaction, but in a way, the bigger way, a two-step reaction, where I have this step, which is the slowest step, right? Waiting for that bond to pop, and then pretty quickly, water is going to come in to form a or to be the nucleophile to form a new bond. Because my slow step only involves one reagent, we're going to call this the SN1 reaction. Still nucleophilic substitution, but now it is unimolecular, because as we'll see in a second, the rate law only depends on one molecule. So let's look at the differences between SN1 and SN2. The biggest difference is rate law. In the SN2 reaction, both my electrophile and my nucleophile show up in the rate law, which tells me that both are important. When I look at the rate law for the SN1 reaction, I only see the thing with the leaving group, the electrophile. The nucleophile actually does not show up in the rate law. Why is that? Well, because this is the slow step, and it does not involve the nucleophile. Only after I go through that slow step do I have the nucleophile involved. Again, if we go back to the picture, the SN1 reaction is this kind of one hump like that. But the SN2 reaction, I've got a big barrier, and then I've got this little well for the cation, and then a little bump, and then like that. Okay? And so, only thing that matters is this initial barrier height, which is only the thing breaking. The nucleophile does not have anything to do with getting over this first hump. So the rate law because the rate law doesn't involve the nucleophile strength is not important. And actually, almost all the time, when I do SN1 reactions, I'm going to have a very weak nucleophile, usually the solvent, often water. The other easy tell between these two is to look at electrophile structure. So in the SN2 reaction, we said that steric hindrance is really important. And so the less hindered something, the faster it is. So you get your methyl, you get your primary, your secondary, no tertiary, right? So if you saw something like this, you'd say, no way are you doing the SN2 reaction. No. However, if you're talking SN1, flip it, right? Because now we're not worried about steric hindrance because nothing is attacking in the slow step. The only thing we're worried about is how easy a cation is that to make. And so I can only do SN1 reactions when that cation is relatively easy to make. And there's basically two scenarios. One where it's tertiary, like this, and another one where that cation is resonance stabilized, that I'll draw in a second. So only that can work. Methyl, primary, secondary, all of the things that worked for SN2 will not work for this one. So again, if you're on a test and you're trying to figure out which is which, this is the easiest tell. If you've got primary, tertiary, or methyl, primary, secondary, that can do SN1, can't do SN2. If you've got tertiary, it can do SN1, it cannot do SN2. This is the biggest dividing line. In addition to tertiary cations being stable, resonance stabilized cations are also available to do SN1 reactions. So here I am looking for leaving groups next to but not on a pi bond. Here, leaving group next to but not on a benzene ring. Or even a leaving group next to something with a lone pair. Why do these work? If I have this leaving group leave, what you can see is a cation like this. I've drawn the p orbitals here. You can kind of see the pi bond can overlap this empty p orbital. I know we usually talk about resonance when it comes to extra electrons, right? Negative charges. But it also happens when I'm short an electron, right? So here, instead of spreading out 4 electrons among 3 atoms, I'm spreading out 2 electrons over 3 atoms. Pi bond here can swing over and fill this empty carbon p orbital, which gives me a resonance structure like that. And so notice I've got 2 positive sites here. So in theory, my nucleophile could attack either this carbon or that carbon to give me 2 different products, not necessarily 50-50 mixture. This middle one is less ambiguous. So here my leaving group is on a primary carbon. So you would think that this would be the worst cation that I could make. But when that leaving group leaves, I get a positive charge next to my benzene ring. Again, I can picture a big p orbital overlapping all the p orbitals on this ring. So I can draw resonance structures that pull a pi bond out of the ring to give me resonance structures like that, and I can keep pushing that charge around the ring every other carbon. So this is actually a really good SN1 reaction and pretty easy to do. This one is the hardest to see. We don't have any pi bond that we can push over, but we do have this oxygen with lone pairs on it. And if I have a carbocation next to a lone pair for something, I can imagine taking that lone pair and just having it lean over. So this is kind of like resonance, but there's only 2 atoms involved. So if that lone pair becomes a double bond, my resonance structure looks like that. It's not really the case that I have a bunch of positive charge on my electronegative oxygen, but it does remind me that this oxygen's lone pair is stabilizing this cation. So when can I do an SN1 reaction? I can do an SN1 reaction when my leaving group is either on a tertiary center like this, or when that cation would be stabilized by resonance, either by some kind of pi bond or arene, or stabilized by an atom with lone pairs that I can draw a resonance structure like this.